If you ever watched a video explaining quantum physics, you were probably extremely confused. These videos make it seem like quantum physics is some mystical, incomprehensible thing that nobody understands. They tell us that particles can read our minds. We've heard that they can exist in multiple places at once. We've heard they can teleport. And we've definitely heard of the famous and horribly overused Schrödinger's cat. It sounds like magic, and honestly that's because they make it seem like magic, and we've been lied to. The universe is not a magic show, and pop science channels just love to use spooky language and misleading animations to get clicks. I'm not going to do that. Today I am going to strip away all the BS and actually explain to you what quantum physics is. There's no magic, no mind-reading marbles, just the actual beautiful and completely logical physics. Let's start off with the biggest lie we've been told, that observing a particle with our mind can collapse its wave function. Pop science channels absolutely love this, and it's because it's spooky and it makes humans sound like some magical beings that can control the universe just by looking at it. But that's not how physics works. The universe doesn't care what we see, and observing something is not a human looking at a screen. Observation is literally just a physical collision. How is that? Well, I'll tell you. Imagine you are in a pitch black room, and there's a balloon floating somewhere in the air. Now you want to find out exactly where the balloon is, but obviously you can't see it. How do you find it? Well, you aren't the brightest, but you come up with an idea. You decide you are going to throw bowling balls into the dark room until you hear one hit the balloon. Finally, after all that work, you found the balloon, but what happened to it? Well, you violently blasted across the room. You could hear it hit the balloon and you know where it hit it, but the balloon is lost again. In the quantum world, a particle, or for our example, an electron, is that balloon. And because it's so incredibly tiny, the only way we can look at it and know where it is by bouncing other particles, like photons of light, off of it. This is what happened in the double-slit experiment. To observe the particles, they didn't just look. It's way too small for that. What they actually did was they shot a laser at each of the slits. And if an electron went through one of those slits, it would fling a photon into a detector and tell you which slit that electron went through. Light is the bowling ball. The moment a photon smacks into the electron to send a signal to our detector, that violent physical collision completely scrambles the electron's path. And that scrambling is what seems to make it stop acting like a wave and become a particle, but we'll discuss that later. The electron didn't change its behavior because a conscious mind watched it. It changed its behavior because we violently rammed it with a particle of light. Measurement in physics is always a physical trait of energy. In the double-slit experiment, the electrons acting like waves and making the interference pattern are like the unbothered floating balloons. But the electrons that get hit by the laser are the balloons that got smacked by the bowling ball. The natural state of a particle is a wide, unbothered ripple of energy, or a wave, and its disrupted state is the hit balloon where its path gets scrambled. The way I was taught superposition is that there is a wave of probability, and inside that wave there can be a particle. But that particle is not confined to one position in space, and in fact, it is in multiple places at once. Now, maybe I didn't understand what I was trying to be taught, but that explanation of superposition is completely false. And the idea that a solid particle can literally be in two places at once makes no sense. If I have an apple, it can't be in my room and in the kitchen at the same time. If we want to understand this, we have to remember one very important thing. An electron is not a solid particle. At the fundamental level, our universe is made of invisible, fluid-like oceans called quantum fields. An electron is just a spread out ripple or a wave traveling through those fields. Now this is where my favorite analogy comes in. The fungus. I thought I came up with this analogy, but it turns out Richard Feynman beat me to it. Think of a traveling particle's wave function like an underground fungal network, like mycelium spreading out in all directions. It's always looking for something to touch and cling onto. It's like those slime mold videos you see on YouTube. And its branches or its arms are like a web of possible places it can make contact with something. This is exactly what superposition is. That web of possible points of contact is a particle superposition. Superposition is not the idea that a particle is literally in multiple places at once. It just means the wave's branches, or its spread, stretch out, and the height of those branches, called the amplitude, determines where that wave is most likely to collide with matter and cling onto. And that collision is what makes the wave become a particle. But where does the idea of it becoming a particle even come from? If it's always a wave, why do we call it a particle? The main reason for this is to make it easier to understand, but honestly, it just confuses people. So what does being a particle even mean? Well, our universe has a strict rule. Energy is quantized, which means it only trades in indivisible, all-or-nothing packets. The detector screen at the back of the double-slit experiment cannot absorb 1% of an electron here and 1% there. It has to take 100% of that electron's energy or nothing. In the microsecond that the spreading mycelium wave touches an atom on the detector wall, an all-or-nothing transaction is triggered. The entire spread-out probability wave instantly snaps shut and deposits 100% of that wave's energy into the single point of contact. This math is represented by the formula PSI squared. It was made by Max Born in 1926, and it tells us that the peaks of a probability wave, or the quantum ripple, are the most likely transaction zones. To someone who doesn't know what's actually happening, it looks like a solid little bullet hit the detector, but a particle is not a bullet flying through space. A particle is literally just the single localized transaction point of where a wave delivers its energy. But if it's always a wave, why does it stop making that cool double-slit interference pattern when we turn on the laser and observe it? Well, let's look at this simulation I've linked in the description. When the wave passes through both slits undisturbed, it splits in half, overlaps and interacts with itself, and forms these beautiful lines. But what if, instead of shooting the electrons from far away and behind the two slits, we shoot them starting from inside just one of the slits? Well, as you can see, the double slit pattern is gone. And if you look at the detector screen, you don't get random static either. You actually get a single slit diffraction pattern. This pattern looks like one bright concentrated band in the middle that gently tapers out on the sides. And guess what? That is precisely what we see in the double slit experiment when we turn the laser on. We see a single slit pattern behind the slit we observe the electron going through. But this pattern only appears when the wave comes from inside one of the slits. How does a photon of light physically force the electron to start its journey from inside just one slit? Well, before the laser is turned on, the electron wave is happily headed toward both slits. But when you turn the laser on, you flood the slits with photons. When the electron reaches slit A, it collides with the photon. And because the universe only trades in 100% whole packets of electron energy, that physical collision forces an instant transaction. This causes the entire spread-out probability wave to instantly snap shut and concentrate right at the point of impact, and that point of impact is inside slit A. But that electron doesn't get destroyed, and it doesn't turn into a particle. What actually happens is it gets kicked, and from that exact microsecond, its wave function resets. It starts a brand new journey toward the back wall, but this time it is originating only from inside slit A. And because it is forced to restart its journey from only one slit, it has no second wave from slit B to overlap with. And no overlap means no double slit interference, and you just get that single slit pattern on the back wall. We didn't just catch a wave, turn into a particle, and try to sneak its way through a door. What we did was we physically disrupted a wave, and scrambled it, we broke its connection to the other slit, and we forced it to start over. The electron never ever stops being a wave, and it definitely never becomes a solid particle. So why did Richard Feynman, one of the greatest physicists ever, say nobody understands quantum mechanics? Well, he wasn't saying that math doesn't work. He was saying that our human language, words like is, was, particle, or split, were invented by cavemen to describe big, classical, macroscopic objects. But when we force those words onto quantum waves, they kinda glitch and we get weird paradoxes. But if you throw away the clickbait and look at the universe as a beautiful, overlapping symphony of waves, it makes perfect sense. The natural state of the universe is a wave, a ripple of energy. And the coolest part, superposition is the only reason we're alive. The chemical bonds holding our DNA together are literally just electron waves in stable, overlapping superposition, holding our atoms in place. Without quantum waves, matter would collapse and life wouldn't exist. So stop letting clickbait channels melt your brain with magic and bad explanations. The universe is weird, but it is beautifully comprehensible. In fact, Albert Einstein once said, the most incomprehensible thing about the universe is that it's comprehensible. If you want to unconfuse more physics topics with me, hit subscribe, and please leave a comment about what concepts we should talk about next. Remember, don't forget to stay sweet, stay curious, and most of all, remember, don't forget to stay sweet, stay curious, and most of all, stay silly. Peace.